Good morning all. Today we will continue with the strain energy problems. So in the last class we were discussing on the strain energy for suddenly and gradually applied load, which is due to axial load or normal stress. For that we derived the equation and we have done a couple of problems. Now again we'll go for another question. A uniform metal bar has a cross-sectional area of 600 mm square and a length of 2 meter. Stress at elastic limit is 170 Newton per mm square. What will be its proof resilience? Determine also maximum value of an applied load which can be suddenly applied without exceeding elastic limit. Calculate value of gradually applied load which will produce the same extension as that produced by suddenly applied load determined earlier. E is given. So here the question, a uniform metal bar has a area has been given 600 mm square. Okay, it's a rectangular bar and length is 2 meter. Okay, if stress at elastic limit, okay, stress at elastic limit sigma E or sigma E is maximum stress is 170 Newton per mm square. What is its proof resilience? Proof resilience, we know, we have already found that equation somewhere here. We found the equation proof resilience, yes, sigma E square by 2E, where sigma E is the stress at elastic limit. So sigma E elastic limit has been given. So what will be the proof resilience? E is given, sigma E is given, so sigma square by E into V, by 2E into V. Okay, now what is next? Determine also maximum value of applied load. So here they haven't given the applied load. What is the maximum value of applied load? Like maximum load which can be suddenly applied without exceeding elastic limit. Okay, so if it is suddenly applied, that means sigma is 2P by A, and if it is gradually applied, it is P by A. Okay, that's all. So given datas, we'll write given datas, area is given, length is given, sigma is 170 Newton per mm square, E is given. We need to find out the proof resilience. Load when suddenly applied and load when gradually applied. Okay, I just need to substitute all these things. Okay, everything is found. V is area into length. Okay, and rest all things, the terms are given. Okay, right? Now next question, an axial blow applied to a bar. The diagram is given. Axial blow means it's a suddenly applied. Okay, shown in figure, produced an instantaneous extension of DL has been given 0.25 mm. What will be the maximum stress and extension in bar B if same blow is applied axially? Okay, so there are two bars A and B and they are having circular cross section. One is having 5000 mm and 25 mm throughout the its length and area. Okay, whereas for this one the diameter is changing. Okay, so for here the extension given, extension happened is 0.25. okay, its area is found out. Okay, 490.87 mm square. So for the second thing, what is our questions? What will be the maximum stress and extension in bar B? We need to find out maximum stress sigma and DL of B. Okay, if same blow is applied, so the same load is applied here, okay, as that of A. So for that we'll find out, we'll divide this into two, section 1 and section 2. Find its area, AB1 and AB2. Okay, So length of second section is, that means B in second section is 300 mm. Okay, right. Now we need to find out the stress in, there are two sections here, first section and second section. This method you might be knowing while you studied MOS. Okay, for composite sections, what you will do, how will you find out the stresses and the elongation happened. Okay, so since it's a blow, it's suddenly applied load, sigma is equal to 2p by A, and E is stress by strain. Strain is dl by L. Sigma is equal to E into dl A by LA. This is in the case of A. Okay, sigma is equal to, you will find out the stress in A. Okay, now sigma is equal to 2p by A, where P is equal to sigma into A by 2, where you find out the load happened in this section A. The same load is applied here also. Okay, now next we need to find out for B. Okay, sigma is equal to P by A for first section. See, for first section P by A B1, and P is equal to sigma B into, see, stress is equal to force by area, right? From that we get this equation. Similarly, sigma B2 is equal to P by, same load is applying here, P by AB2. P is equal to sigma B2 AB2. 1 and 2, sigma B1 AB1 equal to sigma B2 AB2. We'll do this. Sigma B1 by sigma B2 equal to AB2 by AB1. AB2 is nothing but pi by 4 into d square. Here also pi by 4 into d square. One is 25 and one is 15. We'll get a ratio of sigma B1 by sigma B2 equal to 0.36. Okay. Also we know that total strain energy is sigma square by 2E into V. Here it can be expressed as sigma B1, there are two sections, right? So total strain energy will be the sum of these two sections, B1 square into VB1 plus B2 square into VB2 by 2E. From there you will again get an equation having sigma B1 and sigma B2, and if you solve this you will get U is equal to some sigma B2. Okay, since the same blow is applied, the same load is applied here, the energy will be same. Okay, so strain energy is given by sigma square by 2E into V, and for A, sigma you know, okay, V you know, E also you know, you got this strain energy. This strain energy is equated here. Okay, from there you will get the value of sigma B2, and if you solve again sigma B1 you will get an extension of bar is dl1 plus dl2, sigma B1 by E into L B1 plus sigma B2 by E into LB2, dlB is equal to 0.508 mm. Okay, so this is a simple problem, but you need to recollect your MOS, Mechanics of Solids lectures. Okay, thank you.